Here's problem 11.7. In the figure, a 1.6 kilogram weight swings in a vertical circle at the end of a string having negligible weight. The string is 2 meters long. If the weight is released with its zero initial velocity from a horizontal position, its angular momentum in kilogram meters squared per second at the lowest point of the path relative to the center of the circle is approximately. Alright, so here's a mass, and ultimately we want to find the angular momentum. One way to do that is to find its moment of inertia and its angular velocity at the lowest point. So we can do that. Right away we can find its moment of inertia about the pivot point, and that is equal to mr squared for a point mass like this, and that would be 1.6 kilograms times the radius from that point, which is going to be the length of the string. This is going to be our radius in this case, and so that is 2 meters long squared. So this is going to be equal to 4 times 1.6, or 6.4 kilogram meter squared. So that's our moment of inertia for this mass about the center of the circle. Now we want to find the angular velocity, and we can use conservation of energy for that. If we treat this as 2 points, here's point A, which is above the other point, which is point B, and the height between them is this height right here, which actually is equal to the radius of the circle. So the height's going to be equal to 2 meters. And as we compare these 2 points using the one equation to rule them all, we have that the kinetic energy at A plus potential energy at A plus any work done along the way will equal the kinetic energy at B plus the potential energy at B. Well, there's not going to be any work done along the way, so that's going to be 0. The potential energy at B is going to be 0 because we're going to define that height as our 0 height. The kinetic energy at A is going to be 0 because we're going to start from rest. So now we're left with the potential energy at A, which is mg, height at A, is equal to the kinetic energy at B, which is all rotational. So we're going to treat that as 1/2 the moment of inertia times the angular velocity squared. So we can solve this for the angular velocity. We have that omega should equal 2 times mgh divided by the moment of inertia, square root. So that's going to be 2 times 1.6 times 9.8 times 2 over the moment of inertia, which is 6.4, all this square root, and that's equal to 3.13 radians per second. Hence, our angular momentum, which is the moment of inertia times the angular velocity at the lowest point, is going to equal 6.4 kilogram meters squared times 3.13 radians per second at the point B, and that is going to be equal to 20.0 kilogram meters per second, meters squared per second, if I can get this to right. So that is our angular momentum at the lowest point, 20 kilogram meters squared per second. Here's a somewhat alternate way we can look at this. At the lowest point, the angular momentum, in a linear fashion, as it's going this way with some velocity, is going to be equal to mass times velocity times r at that moment, mvr. So, if we found the velocity at the lowest point, which would be the square root of 2gh, that's going to be equal to 2 times 9.8 times 2 square root. That's going to be the square root of 4 times 9.8, which is going to be 6.26 meters per second. Hence, our angular momentum, which is mvr, would be 1.6 kilograms times 6.26 meters per second, and our radius at that point would be 2, and that is equal to 20.0 kilogram meters squared per second. So that also would give us the angular momentum. So two different ways to figure out the angular momentum in this problem, and they're both correct.